And hello again, and today we're back on the 3D10 print program again, and last time we converted it from BBC Basic to run in 6502 assembler using the built-in assembler in BBC Basic, and today we're going to convert it to ARM assembler using the built-in ARM assembler in BBC Basic version 5 for the ARM processor. So before we do that, I'll just load up the 6502 version, and I have the 6502 tube processor selected at the moment. So if we list the program, you can see the basic with the assembly in the middle of it. If I run it, it will assemble the code, and I can call the code that I've just assembled with that, and the effect that you've probably seen 100 times before is displayed on the screen. So I'll now jab the break key to escape out of that, and obviously the first thing I need to do is I need to select the ARM processor. So currently I have processor 24 selected, which is the 6502 with the just-in-time compilation, and I want to select instead processor type 15, which is the native ARM processor type. Now this wasn't a processor type that was available on the BBC Micro. There was an ARM second processor available for it, which I believe was an ARM 1, and I think it was the first ever ARM product available, and it was meant to sort of introduce people to the ARM instruction set and the processor and so on. But we're going to use the native ARM processor, which is the version 7 in the Pi 3A Plus that I have in my PiTubeDirect. So I select that with the star effects command, processor type 15. That will restart the PiTubeDirect with the right processor. Press Control Break, and we're into the native ARM coprocessor running at 1.2 gigahertz. So now I can load up ARM Basic, which is built into recent versions of the PiTubeDirect software, and I can tell it to load and run a program, and I'm going to give it the 6502 assembler version, which has mysteriously failed on line 120 because it tries to load the X register with immediate value of 0, and that's not an ARM instruction, so the program obviously doesn't work. So I need to edit this program. Now the way I've edited programs on the when I was doing the basic and 6502 version was using something called the basic editor, which is a sideways ROM application, and it runs in 6502 machine language though, so it won't run on the ARM processor that I have selected at the moment. So I could fall back on the built-in line editor with the copy key on BBC Basic to do lines changes like that. But that's going to be a bit tedious for me, and it's going to be harder for you to see what I'm doing. So instead what I'm going to do is I'm going to use something called Twin, which is a screen text editor that came on the discs with the ARM evaluation kit for the BBC Micro. It's called Twin because it can edit 2 files at the same time. When I run this command at basic, the basic prompt, it will load it up off disk, or in my case the network file server, and then it will take the program that's in memory, convert it to text, and display it in the screen editor. So I can now go in and insert extra lines of code by doing something like that. When I want to go back to the language I was in this case basic, I press Shift F4. It says, do you want to go back to ARM Basic? I can press Return, and then the code is loaded in with the extra line like that. So that makes editing a lot easier, but we can do better than that. So the Twin command also has an options function. So if I give it Twin 08, that runs the Twin editor but with option 8. And option 8 means strip all the line numbers out before you load them into the editor. So that means I just get the code itself with no line numbers. And this is usually possible in BBC Basic because the Basic is so structured. It's got things like named procedures, repeat until loops, and in Basic 5 you also have things like multi-line if statements, while loops, case statements, that kind of thing as well. So you rarely need to use things like go-tos. So now I've done this, I can just type extra lines in easily by doing that and move things around. When I'm done, again I can press Shift F4, press Return to go back into Basic, and when I list the program you can see my extra lines in there, and it's all nicely renumbered with 10 lines apart. So let's go back into the editor, and every time I load this up I'll try and remember to switch to mode 3 rather than mode 0, which gives me an 80 column mode with 25 lines instead of 32, which I think will make it a little bit easier for you to read, but more importantly it makes the cursor at the bottom of the characters nice and juicy, so you can see where I'm highlighting things as I move it around. So let's just get rid of those two extra rem statements I added. So the first thing I'm going to do before I get onto the code itself is I'm going to increase the amount of memory that I'm reserving for the code. And the reason for this is the ARM instructions are all 32 bits long, whereas the 6502 ones vary between 8 and 24 bits long. So I'm expecting the ARM code to be a fair bit bigger than the 6502 code. So I could just do that, but I'm just going to take advantage of an extra feature in the basic 5 assembler, which if I set a variable like that, and then tell it to reserve memory based on that number of bytes I want -1, because remember the dim statement reserves 1 more byte than you ask for. So that in itself isn't anything I couldn't do in the 6502 version, but something I can do in the ARM version that I couldn't do in the 6502 version is I can set L%. And this sets a limit which says beyond which the assembler will not assemble any more code. So effectively it's kind of a guard address that if I try and write too much code and I overflow the buffer that I've allocated with dim for it, rather than just trample over the variables that follow it in memory, it's going to stop and say limit reached, and the assembler will not assemble any more code. So the way I turn that option on is, apart from setting L%, is I have to change the option to have 8 more added to it. So I've got to change it like that. And that will work, but I'm going to be a little bit fancy because Basic 5 also lets me put in binary numbers with a leading percent. So I'm just going to write my 8 and 11 like that, and I'm going to write my step of 3 in binary like that as well. So enough procrastination, let's move on to that pesky LDX with immediate value of 0 that obviously won't assemble. So what this instruction actually does, obviously it loads the X register with 0, but the reason why we're doing that is we need to create a counter to iterate over the bytes in this block of VDU set. And we start with X equal to 0 to point to the first byte, and then we trundle through the code, and eventually we have printed the last character and we get to VDU set end and we want to stop. So X is going to represent the character number through this block that we're printing out. So when it comes to registers, the 6502 only had A, X and Y, and what you could do with each one was quite limited, particularly X and Y. On the ARM you've got 16 registers which are R0 to R15, although you can't use R14 and R15 because R15 is also the program counter and status bits on certain versions of the ARM, and R14 is something called the link register, which we'll come on to in a moment. But I've got R0 to R13 available for me to play with. So what I'm going to do here is I'm going to use R2 to store what X was previously being used for. So what I want to do is load the value 0 into R2. So the way I do that is using the mov instruction, which is short for move, and then I tell it what register I want to put the result into, and then I tell it what I want to load into it. So this is going to put 0 into the register R2. The next thing we need to do is use this indexed load, so which loads the A register with whatever byte is at the address of VDU set, which is the base of that table of bytes, plus X. So in the ARM, the way you read data from memory is using the LDR instruction, load register, and that will normally load a 32-bit value from memory, and it must be aligned on a 32-bit boundary as well. But we actually only want to load a byte of memory in, and the way you do that is by putting a B after the LDR instruction. So this won't actually operate any quicker, but what it will do is only load the bottom 8 bits, and it will blank out the top 24 bits of the 32-bit register. And in addition, when you've got the processor in certain modes, it won't complain if the address you're trying to load from is not on a 32-bit boundary as well. So once we've issued the instruction, we need to tell it what register we want to load it into, and I'm going to load it into register R0. And then you do the indexed load by using square brackets, and you give it the base address, VDU set, and then you give it the index or the offset from that address, which is going to be an R2, and then close the square brackets. So that would be nice, except that doesn't actually work because you can't put an address in here. If you want to do an indexed load like that, the two addresses need to actually be in registers. So what I actually need to do is I need to put VDU set into a register, and the way you put an address into a register is you use something called the ADR instruction. So this says I want to move an address of something into R1, and the address I want to move in there is VDU set. So if we do that, we can now go in here and change that to be R1, R2. So that's going to load R0 with the byte at the address given by R1 plus R2. Then what we want to do is call the operating system function to print a character on the screen, and in the 6502 we did that by just jumping to a subroutine. On the ARM you normally call operating systems with something called a software interrupt, and you do that here, SWI, and you give it the name of the operating system function you want to call, which to print a character is called OS write C, OS write character. So although I'm giving that a string, what actually happens with the assembler is it calls a function to find out what the number of that interrupt is with that name, and it will then store that in the instruction. So this isn't sort of parsing the string every time the instruction runs, it just stores a number. So that does basically what the following line does. What we now need to do though is we need to increase X to move on to the next character, and X of course is an R2, and we don't have an increase instruction on the ARM, but we do have a sort of general add instruction which takes 3 parameters. So we start by doing add, and we say what register we want to store the result in. Well, we want to store it in R2. What we want to add together, well, the first thing is R2 and the second thing is the immediate value 1. So what this is going to do is add together R2, the value 1, and store the result in R2. So effectively it's going to increase R2 by 1. Then what I want to do is find out if I reach the end. So the way I find out if I reach the end is, has R2 reached the number of characters in that block that I want to print out? So I do a compare of R2 with the value VDU set end minus VDU set. So that's going to calculate the number of bytes in that block, and then when R2 reaches that number, we're going to get the Z bit set, which will mean we can test for that and decide whether to go around the loop again. So when the Z bit is not set, i.e. we haven't reached the end, we do a branch if not equal, which coincidentally is the same as the 6502 instruction, and we say I want to go back to the loop. So in other words, this is going to go round and round the loop until R2 becomes the number of bytes in the block, and then it's going to stop. So that basically does the same thing as the following line. Right, now we move on to the random number generator seeding, and this is achieved by reading the operating system interval timer, which is basically a clock that ticks up once every 100th of a second. And we have the same function available on the ARM, we just have to call it slightly differently. So the first thing we do is we tell it which OS-word call we want to make, which we do by loading R0 with the operating system or the OS-word call number that we want, and we want OS-word call 1, which is basically this is the same as the LDA one. Then what we need to do is tell it where's the block of bytes that we want to store the result in, which we allocated at the end of the code here, this run buff thing. So we don't need to mess about splitting the address over 2 registers because all the registers are full 32 bits in size. So what I'm just going to do is say load the address into R1 of run buff. So that's going to do the same thing as all of this shenanigans loading X and Y with the 2 parts of the address. And then to trigger the OS word, we just call software interrupt OS word, and that's going to do the same thing as all of that. So that's going to get the interval timer into run buff. Okay, so now we move on to the sort of main part of the program. So I needed to store various values before, and because we've only got a few registers on the 6502, I was storing some of the effectively the variables in certain memory locations. But because we've got loads of registers available, I'm just going to use some registers to store the things that previously I was storing in memory locations. And I'm just going to make a little comment here to remind myself what things I'm storing in what registers. So the first thing we need to do is store B, and I'm going to store B in R1, so I'm just going to make a note of that. So we want to start by initializing B to be 0, so we just do move into R1, the immediate value 0. So that just does the equivalent of that. Then we move into main loop, and we need to EOR B with 128. So that's easy. We've got an EOR instruction, which works very similar to the AND instruction. So we tell it where we want to store the result in R1, and then give it the two things we want to exclusive altogether. So the first thing is R1 itself, and the second thing is the immediate value 128. So that basically does the same thing as all of that loading, eoring and storing again. Okay, the next thing we need to do is we've got this counter for the columns across the screen, and we stored that in the Y register. Now I'm going to use R2 to store what was previously in the Y register, so I can just do move into R2 the number 40, very similar to what I did before. The next thing we're on to row loop, where we need to do this exclusive OR again. So I'm just going to sneakily copy that line there, get rid of that. So I'm just basically going to do that again. And then we're on to this bit where we need to get a random number. So we need to jump to a subroutine to get a random number, and we have this linear feedback shift register function, and I'm going to convert that in a moment. But the first thing we need to do is jump to it. Now you use BL to jump to a subroutine, which is called branch with link. So what that does is it uses the link register that I'll come on to in a moment. So we just tell it jump to this address and store the return address in the link register, which I'll come on to. So that's the first bit of the the equivalent of the JSR. Now we'll go on down to that part of the code, and we'll gradually convert that into ARM down here. Now this is a bit of a horrible mess, the way I'm going to convert this, and the reason is because this linear feedback shift register function assumes that all the operations performed on it are using 8-bit registers, and things nicely all sort of roll into carry bits and things like that. But on the ARM, because all the registers are 32-bit, we have a little bit of shenanigans involved in sort of moving things around and getting the right bits to end up in the carry bits for adds that come on later on. So what I'm actually going to do here is I'm going to convert it into a sort of direct equivalent in the ARM, which is going to look pretty nasty. But towards the end of the video, we'll come back and we'll change it into something that looks more ARM friendly, which makes it a lot neater. So the first thing is the reason we've got this run Z is it instead of rund. The reason why I call this here is because this clears the carry flag, and we need to do that because we're doing things like ands and rotates and so on, and we want the carry flag to be 0 to start with. Now on the ARM we can selectively choose whether the carry flag is involved in things like an add or a subtract or whatever. So I don't explicitly need to clear the carry flag when I start, so I can get rid of that bit. Now the next bit, we need to load the accumulator with what's at the address of rundbuff. So again, I'm going to make a little note of what registers I'm going to use here. So I'm going to use R0 to do the same thing as the accumulator. So we start by loading a byte into R0, what's at rundbuff. Now the next thing we need to do is we need to rotate R0 by 1 bit to the left. Now there isn't actually an explicit rotate instruction on the ARM. Instead there's a thing called the barrel shifter, which allows you to perform a normal operation but rotate one of the operands by a number of bits in a certain way, and you can choose that. So instead of explicitly rotating, what you just do is you move into R0 whatever is in R0, but you logically shift it left by 1 bit. So that's going to do the equivalent of moving everything to the left. And this is a logical shift rather than a rotate, but the rotate bit doesn't really matter because the point of the rotate is to swap the carry bit into the bottom bit here, but we know that's always going to be 0 because we were clearing it before. So it doesn't actually matter, we're just shifting instead of rotating. So that's going to shift everything to the left, but the thing it is going to screw up on is the 8th bit of the original value would have slid into the carry bit with the rotate instruction on the 6502, but in this case, because the registers are 32-bit, that bit just ends up in bit 9, and we need it to end up in the carry bit so that when we do an add in a moment it gets involved. So the easy way to do that is to use something called the test instruction. So the test instruction isn't actually, I don't really care what the instruction is, but what it actually does is AND together the two arguments. And what I'm going to tell it to do is I'm going to AND together R0 with R0, but I'm going to logically shift left the second argument, the second version of R0 by 24 bits to the left. And that's going to have the effect of sliding the 9th bit all the way off the end of the 32-bit register into the carry bit. So we don't really care what the AND operation that's performed there is. All we really care about is that the 9th bit ends up in the carry bit, and then the result gets thrown away. So that's going to kind of do the same thing. The next thing I'm going to do is I'm just going to do an AND of R0 with itself and 255, and that will mask out everything but the bottom 8 bits. And the reason I want to do this is when I do the add in a moment, I don't want the 9th bit that just got had the 8th bit shifted into it with this LSL. I don't want that bit to affect the result of the add. So I'm just going to clear all the bits except the bottom 8. So we know we're only doing an 8-bit add in a moment. And then the final thing I want to do is do the equivalent of the TAX. I just need to store A, or R0 in this case, in another register, and I'm going to use R8 for that. So I'm going to use R8 for what I would store in X. So I'm just going to do move R8, R0. So I'm going to copy R0 into R8. So all of that has basically just done these 3 instructions, the LDA, the R, rotate left, and the TAX. So it's pretty horrible, but as I said, that's because we're trying to implement 8-bit operations on a 32-bit processor. Okay, so now we've got the next bit to deal with. So we want to add to R0, which is what previously was in the accumulator, whatever is at the address of rundbuff plus 2. Now, you can't do things like add with an address, you can only do it with a register. So if I want to operate on a register and add something together, I first have to load that value into a register so I can then add it to something else. So I need to actually involve another register here. I'm just going to call it R9 and declare it as sort of a temporary register. And I'm going to use that to load in what's at rundbuff plus 2. And now I've got it in R9, I can use an add with carry, store the result in R0. I want to add together R0 to R9. So that's going to basically do the add with carry. Then the next thing I want to do is I need to get that carry bit that's just been, if I added together 2 numbers that were bigger than, that together became bigger than 255, I've just set the 9th bit, and I want that to end up in the carry bit again, a bit like when I shifted left up here. So to make sure that ends up in the carry bit, I'm going to do the same thing again. I'm going to shift R0 across by 24 bits, which will shift that 9th bit all the way across the 32-bit register into the carry bit. So the next thing, I think I've done all of the adding and the shifting now. I just need to store the values again. So I'm just going to use store register, and I can put B on the end. So this is like the opposite version of LDRB. So this is store register as a byte, and I want to store that byte. I want to store R0 in rundbuff like that. So this stores R0 at the address rundbuff, and I want to store R8, which was X before, in rundbuff plus 2. I find these instructions a little bit confusing because in all the other instructions the first operand is actually the destination for the result, whereas in the store instruction the destination is actually the second location and the first operand is the source. So that's a slightly odd instruction, and you just have to remember which way round it works. Okay, so I think that has done that second line, and we can move on to the this final line here. So the first thing I want to do is load, well, I was loading the accumulator with rundbuff plus 1, but of course we're using R0 to do the same thing, so I'm going to load a byte into R0, what's in rundbuff plus 1. Then I need to do move that into the X register, and of course the X register we're storing in R8, so I just say move into R8 what's in R0. Then what I'm going to do is I need to do this add, and again we have to load that value into a temporary register because we can't add something at an address directly. So I'm going to load into R9 what's at rundbuff plus 3, and then I'm going to do an add with carry R0 into R0. Into R0. We're going to add together R0 and R9 again, and I'm going to store a byte of results into in R0 into rundbuff plus 1, and I'm going to store what would be an X but is in R8 now into rundbuff plus 3. So you notice the add instruction, there's two versions of that. Previously in the code I was using add with two Ds, and that doesn't involve carry. Here I do want to involve carry, so I have an instruction ADC, which means add with carry. So again, I can selectively choose whether I want to involve carry or not. I don't have to go around clearing the bit before or after doing the addition like I had to on the 6502. So that should have done that line there, and now we want to return from the function, and this is where the link register comes in, the R14 register. So when you call a function, what you call a subroutine with BL, branch with link, on a 6502, the way you would do this is you would push the return address onto the stack, and then when you're ready to return, you'd issue an RTS that would read it back off the stack. On the ARM instead, what happens is the return address gets stored in register R14, known as the link register, and all you need to do when you return is you just move that address in R14 back to R15, which is the program counter. So effectively you do this, so move the link register in R14 into the program counter in R15, but you can use two little shorthands for these registers because they get used that way, so you can just say move the link register into the program counter. Now the reason they did that is because quite often you call a subroutine and you don't want to call another subroutine beyond it, so this avoids you having to write out to memory and read back in from memory the return address. It makes calling a subroutine a lot quicker. Obviously, if I wanted to call another subroutine from this one, I would have to store the link register somewhere so it's not lost and I can return back to the right place. And there is some instructions to push and pop from the stack, but you have to do that explicitly yourself if you need to do it. But I don't in this case. I can just use the link register directly and just restore it when I'm done. So I think that's the ranz function done. So we can move back to the main loop and continue on from what we need to do after calling that. So after we called the run0 function, we want to get this z variable, and the z variable is either 0 or 1, and we do that by just looking at the least significant bit of what is the first byte in rundbuff. So in this case I need to store z somewhere, and I'm going to use another register for that. So I'm going to say R3 is going to be what is z. So what we then need to do is we need to load the byte into R3 what's at rundbuff, and then we just need to do an AND to mask out every bit except the least significant one. So I can do AND, store the result in R3, I want to AND R3 with the number 1, so that's going to do that masking out. So that does the equivalent of that line there. Okay, so now we move on to the bit where we set the colours. So this is quite straightforward. We just set R0 to 17, all software interrupt, OS write C. So that's going to print character 17. That is the set colour VDU control code. So that does the first one. The next one we need to do a bit of calculation on. So we need to start by moving into R0 the number 130. Then we need to do this subtract of B, and before we had to explicitly set the carry flag because what we wanted to do is subtract B and nothing more, because if the carry flag is clear then B plus 1 gets subtracted. We just want to subtract B, but we can just do that with the sub instruction. Again, like the add one, there are two versions. There's subtract with carry that looks the same as the 6502 one, and then there's sub that does the version without carry. So this one's fine for us. So I'm going to say put the result in R0, and I want to subtract R0 from B. Subtract B from R0, so I'm going to do that. So that's going to set R0 to be R0 minus R1. So that's going to do the calculation we need, and I'm going to print that character out. So the next thing I need to do is print character, delete that line. Next thing I need to do is print character 17 again, so I'll just copy that and put that copy down there. That does the same thing as that. And then what we need to do is do this sort of multiply and add and all that kind of stuff here. So the first thing I want to do is I need to get hold of Z. So I'm going to move into R0 what's in R3 because that's what Z is. Then I need to shift it left by 1 bit. So I'm going to do move R0, R0, logical shift left by 1 bit, which will work, except as I explained earlier, you can use the barrel shifter on any instruction, so there's no particular reason to do this like this when the instruction before is just moving R3 into R0, because we can combine these two and just say, well, I want to move R3, left shift it by 1 bit and store the result in R0, can do that all in one instruction. Next thing I want to do is add on B, so that's quite easy. We just say add, store the result into R0, what is in R0 plus R1. Now we took advantage of the fact that the add comes with carry on the 6502, and we set carry here to explicitly add one more than B, which is what we want to do. There isn't an easy way to set the carry bit here and use add with carry instead. Well, not in a way that's any more efficient than just adding one explicitly, so I'm going to do that. So I'm just going to say add R0 to 1 and store the result in R0. So that's going to do the same thing as that. Then I'm going to print the character in R0. So that does the other control character for the color. And now we move on to printing the custom character, either 240 or 241. So this is quite easy. We move into R0, the value 241, and then what we want to do is just subtract Z from it. So we say subtract, store the result in R0, and I want to subtract R0, take away R3, so this will store in R0, R0 minus R3, and then I'm going to print that character out. So that does the same thing as that, and we move on to the final 2 lines of the code, where we need to decrease Y, which is the counter along the rows, along the columns along the screen. So we're going to decrease it by 1. Now there isn't a decrease instruction in the same way there's not an increase one, but instead we just do a subtract. So I can say store the result in R2 of taking R2 and subtracting 1 from it, and then if we're not equal to 0, i.e. we haven't got down to 0, so we haven't reached the end of the row, you need to go back to row loop. And if not, and you just if you have reached the end of the row and you want to go back and start a new row, you just branch unconditionally back to main loop, and you do that with the B instruction on its own, branch, which always looks a little bit sort of wrong to me, like there's a few letters missing out of the instruction. So that should be all of the code converted. I'm just going to change that at the end to ARM, and also up here I defined these variables with the location of OS write character, OS word, B and Z, and I'm not using any of those, so I'll just remove those lines. So let's quit out into ARM Basic, save it, run it. Fortunately it all assembles, and we'll run the code and it doesn't work. The effect is wrong. Now I'll admit I did this deliberately. I go back into the old into the program, and the reason for this, why that isn't working, is to do with this final subtract that we just converted. So if I move down to this subtract in the loop, and this is because apart from instructions that explicitly do only sort of tests and comparisons like CMP and TST, all the other instructions don't affect the condition codes like the Z bit, the Z condition flag to say that two numbers are equal or things like that, unless you explicitly ask them to. So this subtract will do the subtract, but it won't set the Z flag that we're looking for in branch with not equal when it reaches 0, unless we tell it to do that, and we do that by putting an S on the end of the instruction. That may sound a bit strange, but there are reasons why you wouldn't want to do that in some cases, and in fact we'll have a look at one of those in a little bit. So this will do the subtraction, but it will also set the Z flag if R2 becomes 0, and that will enable the branch conditional checking here to work properly. So let's just save out to basic again, run the program, execute the machine code, and we get the effect. Unfortunately everything's working, so that's a relief for me. So I'll just get break, get the program back and go into the editor, and we'll start having a look at ways in which we can change the code and make use of some extra ARM features. So the first thing we're going to look at is this loop that sets up the screen mode, defines the colors and the custom characters. Now on the 6502, we had to use this indexed addressing mechanism because we've got 16-bit addresses but only 8-bit registers, so we can't store an entire address within a register and increase it. Instead we have to use this offset mechanism. But on an ARM we've got 32-bit registers and 32-bit addresses, so we can store an entire address within a single register. So instead of using this indexed addressing mode, I can instead just load up R0 with whatever's at R1 and increase R1 after doing so. I don't need to use the offset addressing. But we still have a problem that we need to work out when we've reached the end of the block. So the way I'm going to do that is by loading the address of the end of the table of bytes to be printed into register R2, and then I can work out when I've reached the end just by comparing R1 with R2 like this. So let's just save that out and run it. And there we go, the program still works. So that's fine, and we've made use of the 32-bit registers in the ARM and avoided the indexing, but we haven't actually saved any instructions. The program's still exactly the same size and probably takes the same length of time to run. But what I can do is make use of a feature in the LDR instruction called post-increment. Now with this I can stick an extra parameter after doing the load, and what this means is load R0 up with whatever byte is pointed to by R1, and then after you've done that increase R1 by 1. So it will effectively do the add that's on the following line all in the load instruction. So if I save that out, run it and execute the code, you can see the program still works. So there is also a pre-increment mechanism where you can increase the value in the register before you do the load and then optionally update the register afterwards, but we don't need to do that here. So you may look at that though and think, well, why am I loading this address into R2? Why don't I just compare the address directly there like I was doing when I was comparing the offset? Well, the reason for that is that the ADR instruction doesn't actually work the way you think it does, and I'm not going to go into that right now. I'll come on to that at the end, but for now I'll just put the program back to how it was and compare R1 with R2, and then we'll move on to the next thing. So let's move down to this main loop where we're setting colours and printing custom characters, and in particular this line just below set colours, or two below set colours, where what we're doing is we're taking number 130 and then subtracting R1 that contains B from it and printing the result. We're using two instructions to do this, but actually the subtract instruction already takes three operands, which is the destination, the number we want to subtract from, and the final one is the number we want to subtract from it. So instead of loading 130 in separately, can't we just put 130 in as the second operand and get the whole thing done in one instruction? Well, unfortunately not, because the only operand that can actually be an immediate value is the final one. The first one, or the second one, the number you're subtracting from, that always has to be a register. So I could put the R1 there and then leave the 130 on the end, but then the problem is I'm doing the subtract in the wrong order. So instead of subtracting R1 from 130, what we're now doing is subtracting 130 from R1. But that's actually okay, because there's a special version of the subtract instruction called reverse subtract, and this uses the operands in the opposite order. So this one will take the third operand and then subtract the second one from it and store the result in the first one. So this will do 130 minus R1 and store it in R0. Moving down a couple of lines, we've got this sort of complicated move with a shift left to do the multiply by 2, and then we're adding on R1 and then adding one more. Can we combine this at all into any fewer instructions? Well, we can do, because we can use the barrel shifter with the add instruction as well. It's just that the only thing we can use the barrel shifter for is the final operand in the add. So if we want to do that, we're going to have to put R1 as the second operand, the first number we want to add, and then we can put the final one there and shift it all in one instruction, removing that separate move. And of course, with add, it doesn't matter what order you do the operands in, because the result's always the same if you swap them around. So there's no such equivalent of like a reverse add for that. And then finally, the next line here where we're printing the custom character, we're just doing 241 minus R3, and we can rewrite this one using a reverse subtract like the one above. So we can just do that and get rid of the separate move. So if we save that out, run it to assemble it, call the code, get the same effect so everything's still working, and we can go back into the editor. And overall there we've saved 3 instructions, and of course more importantly we've sped things up, because that's something we're critically obsessed with here. So now let's have a look at the loop in the main part of the program. And there's actually two loops here. There's one called main loop, and we reach that every time we begin a new line across the screen. And each time we do, we exclusive OR R1 with 128 to flip the top bit, and we reset the counter for the number of columns remaining in the row to 40. And then we flow into the inner loop, which we also reach every time we move to another column across the screen. And there we exclusive OR R1 with 128 as well. So what happens here is every time we go around the main loop at the start of a row, we're actually doing this exclusive OR twice. So effectively we're not doing it because we're toggling the bit and then toggling it back again. So if we look at the end of the loop where we do this conditional branch after doing the subtract to work out how many columns are remaining in the row, instead of doing this branch if not equal to row loop, we can get rid of that and just jump back up to main loop. So when we jump up to main loop, we're going to arrive here regardless of whether we've begun a new line or not. But the difference is that when we've begun a new line, the Z bit will be set to 1, and when we haven't begun a new line, it will be cleared. So what we can do here is we can take advantage of that and the conditional execution feature on the ARM. So on the ARM, all instructions can be conditionally executed based on the condition codes. So what I can do here is I can say exclusive OR, but only if not equal, i.e. the Z bit is not set. So this will only run when we're not at the start of a row. The move, on the other hand, we only want to set when we are at the start of a row, so that'll be when the Z bit is set. So there we can do move EQ. So that will only run now when we are at the start. And that means we don't need this separate label and we don't need this separate exclusive OR. So we've got rid of a couple of instructions in a loop and taken advantage of this conditional execution feature. So if I now save the program and run it and call the code, we get the same effect. So the program's still working. If we go back into the editor and have a look again. So this is more than just removing a couple of instructions. I think it matters less now because instruction processors are better at doing sort of predictive execution. But when the ARM was first invented, there was a pipeline of instructions to be executed, and every time you do a branch, you disrupt that pipeline because it's sort of partway through in executing the various stages of instructions, and it has to be flushed, and you have to restart everything again, and that actually causes a performance hit. And that's actually the same on processors like the 6502 and so on, I think. So what we're doing here though is we're never really disrupting that pipeline because we don't jump around differently depending on the situation with different codes. We're just continuing the program execution like normal. It's just sometimes we do something and sometimes we don't. So not only is this making the program slightly smaller, it's also improving performance. And this is also why that S bit is quite helpful on the end of certain instructions, because when you don't need to affect condition codes, you can leave it off, and then you can leave the condition codes alone to take advantage of this conditional execution feature on certain instructions. So there's one final thing I need to do before I move on to the next optimization, which is that at the start of this loop, I need to ensure that the Z bit is set, because otherwise, when the program goes through it the first time, it's going to do this exclusive OR, which probably doesn't matter too much, but more importantly, R2 isn't going to get initialized to 40 columns and might end up with some other strange number in it. So I don't know how I've been lucky so far, but maybe this seed random number generator function always ends up setting it. But what I can do if I look up a little bit further in the code is when I use this loop to set up the screen mode colors and define the characters, we always exit this loop with the Z bit set, because if it isn't set, we branch back round to print the next character. So if I just do a little bit of shuffling around of the code to move that function after the seeding of the random number generator, we now know that the Z bit is always going to be set and the program should run correctly each time. So let's just confirm I haven't broken it. But there we go, it's still working. So I guess we were just lucky before. Okay, I've been putting it off too long, but it's now time to tackle that linear feedback shift register random number generator subroutine. So when I ported this from the 6502, I followed it fairly closely, and I was explicitly loading and storing the bytes from the run buff memory locations each time. But we've got lots of registers on the ARM, so we might as well make use of them. So instead of using that run buff memory, I'm just going to instead just store run buff each of the bytes in registers R4 to R7. I still need R8 to hold what we'll be using the X register for on the 6502, but I don't need R9 because we don't need to read from memory and then operate it on, because the values are directly available in the registers. So if we start moving the code, we don't need to do this load. Instead, we can just operate directly on R4. The test, we can operate on R4, and the AND, we can operate on R4. And then when we move into X, we're just moving R4 directly, which is containing runbuff plus 0. Next one, we don't need to load that in, runbuff plus 2, because it's available directly in R6, so we can do the addition using that. The test, again, we can use R4 directly, but we don't need to do these stores because the results are already held in the registers. But what we do need to do is we need to AND R4 with 255 to mask out everything other than the bottom 8 bits. And that's because this add instruction at the start of the line here may have set the 9th bit when it did the addition. Now that didn't matter when we were using the store byte instruction because we were only saving the bottom 8 bits there. But now we're keeping hold of the full 32-bit value in the register. We need to make sure that 9th bit isn't set, so we use AND to mask it out. And the final thing is we need to store back in runbuff plus 2, which we're holding in R6. We need to store what we were keeping temporarily in X, which is in R8, like that. So moving on, we don't need to do that to load from memory because what we want is available directly in R5. And similarly here, we don't need to load R9 with runbuff plus 3 because that's already held in R7. And similarly, we don't need to do these store bytes, but we do need to do the ANDs for the same reason as above, just to mask out everything other than the bottom 8 bits. And we need to move into runbuff plus 3, which is held in R7, what we were temporarily storing in R8. So get rid of that. So that's good, that's shrunk the subroutine down a little bit, but we do have to make some changes elsewhere to make use of it. So the first one is when we seed the random number generator up here. So this was just reading the system interval timer into runbuff, and we were loading and storing data from there every time we ran the random number function. But now we're operating on the registers. We need to get what we've just retrieved into runbuff and store it into the registers. So there isn't really an easy way to do this, short of just doing a lot of these. So I'm just going to load runbuff 0 to 3, each of the bytes into registers R4 to R7. And finally, the other thing I need to do is when I use the random number generator function and retrieve the result, I previously was loading R3 with the data, the byte that was at runbuff, and now of course that's directly available in R4, so we can just get rid of that load and change the AND instruction to use R4 directly. So I've lost some instructions, but I've also gained some instructions. I'm not sure what the aggregate total is. I think I'm still down, but of course the really big thing is that with this code is that the extra instructions that I've had to add in are up here and executed only once, and we've removed an instruction from here as well in the middle, and probably more importantly, this subroutine now operates entirely using registers in the processor with no memory. So that speeds things up enormously because we don't need to keep reading and writing memory, which is much slower than the registers. So if we just save things out and run to assemble, call the code, and it all still works. So that's improved things. That said, we haven't really improved things massively. I mean, we're still basically trying to run an 8-bit linear feedback shift register subroutine on a 32-bit processor, and we're doing a pretty sort of nasty job at it as well. But what I was thinking was we don't actually care what this function does at all. What we really care is just that it yields random numbers. So I was looking through the ARM Evaluation Kit instruction manual, and in the back are a bunch of appendices, and one of which contains a series of example subroutines. And one of them was a linear feedback shift register function. Now this used a 32-bit register to hold 4 bytes of information. So I'm going to use R4 for that. Rather than splitting each byte across 4 registers. It also needs a 5th byte, which I'm going to store in R5, and that's going to be runbuff plus 4. And remember, the operating system interval timer Oswald1 call returns 5 bytes of information, so we're actually going to get that byte automatically from that function. And then we need a temporary register to hold things in as we're sort of shuffling them around. So This routine is entirely different, so I'm just going to delete the old one. And like the previous one, I don't really understand how this works, but I can at least type it in. So I'm just going to do that now. It makes use of something called a rotate right extend, which is an operation on the barrel shifter that rotates all the bits right, and it only can rotate by one bit at a time, but it rotates right through the carry bit as one of the things. So it rotates right through 32 bits. And then it involves a couple of logical shifts to the one to the left and one to the right, and then we return. So that's the routine change, and obviously it's a lot smaller, and it's going to run a lot quicker. The only thing we need to do is, before we can use it, we need to change how we load the data into the registers. So instead of loading the 4 bytes of run buff into these 4 registers, we want to load those 4 bytes into register R4 itself. So that's really easy. We just delete the B there, and that loads a whole 32-bit word instead of one 8-bit byte. And we also need to load into R5 what is at run buff plus 4. So I can just change that. So that shrunk that and shrunk the routine as well. So let's just save it, run it, and execute the code, and we get the same effect. So I mean, technically we're getting different random numbers, but I mean, hopefully we always get different random numbers, so it doesn't really matter. So let's have a look at that ADR instruction, and in particular this one near the start of the program that loads the address of run buff into register R1. Now if you think about it, this instruction does something quite amazing, which is because the ARM has 32-bit registers and 32-bit addresses, and it also has all of the instructions being 32 bits long. And somehow this ADR instruction manages to encode not only the opcode for the ADR and the register R1 as the destination, it also manages to squeeze in a 32-bit address all into one 32-bit instruction. So let's just check that it really does do that by running the program and looking at the assembled code. And there's the ADR instruction, address 9478, and just to the right of that address you can see the hexadecimal of the assembled instruction code, which starts E28. And indeed it does seem to have fitted the whole ADR instruction into one 32-bit instruction. So let's have a look at the rest of the code, let that assemble, and you can see the address of run buff is at 9522. And now we can use the disassembler that's built into the ARM native coprocessor on the PiTubeDirect, and we'll have a look at the code starting at the first address of the program, 9474. And from there we can see again at 9478 there's that ADR instruction, and it does indeed seem to load the address 9522, that of run buff, into register R1. But if you have a look at the hexadecimal of the instruction code next to it, the E28 number, it's slightly unusual because you can't see the number 9522 in there, which is odd, because if you're used to looking at the 6502 machine code, then and you do something like a load or a jump, then you'd see the opcode for the instruction, and then somewhere in there you'd see the address that you were trying to jump to or load from. I mean, it might appear backwards because the 6502 is little endian, but you'd still see it in there somewhere, and it doesn't seem to appear in the ARM assembly code. So what's actually going on here? Well, the answer is that that instruction, the ADR instruction, doesn't really exist. It's actually a pseudo instruction used by the assembler. And what happens when you use it is the assembler will translate that instruction into a different instruction depending on what the address is that you're trying to reach. Now in this case it will change it into an add instruction where the result of the add is going to be stored into the register where we want the address, and the first operand of the add is going to be register 15, the program counter, i.e. that of the current instruction, and then it's going to be an immediate value, which is the number of bytes away from the current instruction that the address we're trying to reach is. In other words, run buff minus p%, because p% contains the current instruction's address in the BBC Basic assembler. So what this is going to do is calculate that address by taking the current address and adding on the number of bytes further along in the program of the address we want to reach is. Now you also have to subtract 8 from this because of pipelining on the ARM, and this is because when this instruction actually executes, the ARM will be reading in the instruction 2 further along, this LDR instruction, and the assembler will need to take account of that, and it does that for you automatically when it computes the add offset. So if we quit out, run the program again, we can see that the ADR instruction is at 9494 and the add instruction is at 9498, and that the assemble machine code looks very, very similar for both instructions. In fact, the only thing that differs between the two is the final byte of the instruction, which is A6 for the ADR and A2 for the add. And the reason for that differing is because the add instruction is 4 bytes further along in memory, so the distance between it and run buff is 4 bytes fewer, so the offset is slightly different. Now if we let that finish assembling, now we can see that run buff is at address 9542, and we can disassemble the code starting at 9490 this time. And now we can see that at 9494 we've got our ADR instruction, and at 9498 we've also got an ADR instruction. Now both of these instructions are actually add instructions. It's just that most ARM disassemblers will recognize this pattern of adding together an immediate value with the program counter and translate that into an ADR instruction, because that's probably what the programmer intended, and it's a more useful way to display the instruction. Now suddenly, if we look at those numbers, they start to make sense. So if we take the address of run buff and subtract the address of one of the instructions, the first ADR instruction, and we subtract the 8 to allow for the pipelining and display the result in hex, which is the tilde at the start, we get back A6 as an offset, which equals the hexadecimal number stored in that ADR instruction up here. So the rest of these numbers, I mean, they're all things like the E28 is all part of the add opcode and the condition codes if we're using conditional execution, that kind of thing. The F is the one of the operands that we're adding together, so 15, because one of the operands is the program counter. The 1 is the register we want to store the result into. So this all starts to make sense. You can actually see that at 94A0 the LDR instruction uses a similar trick. It's just that this particular disassembler doesn't translate that into the same sort of friendly address, but another disassembler might do that. Now there is some limitations with this mechanism, which is that you can't reach all addresses because you've only got a small number of bits to include to encode this offset. So for example, if I try and reach an address that's FFF0 away from the current instruction, then we get this error, bad immediate constant. But we can, oddly, reach an address that is just slightly bigger than that. And the reason for this is the way that immediate values are encoded on the ARM. They aren't just stored as a flat set of bits, they're stored as a set of bits plus an offset to shift them by. And this lets you reach a larger range of numbers, although you can only use a certain number of bits in a row to be set and cleared. If you want to reach an address that's further away, there are tricks involving a couple of adds or storing the address at a location nearby in memory and using an indirect load to get that into the register. And if run buff appeared before the current instruction, then a sub instruction would be encoded instead of an add. So there's one interesting side effect of this, which is that if I just remove that add line again and run the program to assemble it, all the addresses in the program aren't encoded absolutely, they're all encoded relative to each other. So this means that there's no need to actually relocate any code if you want to move it somewhere else in memory. So if I save this program out to disk, or the file server in this case, and I load it back at some completely different address, like 60,000 hex, I can actually execute the program and I don't need to do any sort of relocation to change the addresses, because all the operating system functions are caused with software interrupts, and the addresses to reach different parts of the program are all done relatively. So the program indeed runs without me needing to do any sort of relocation on it. Okay, so I like to give you the Steve Jobs just one more thing ending, because we've got this beautifully hand-optimized ARM assembly that runs nice and quickly, but we're kind of slowed down a bit by this 8-bit video hardware in the BBC. So is there anything we can do to speed that up? Well, the Raspberry Pi itself has an HDMI output. Can we use that somehow? Well, since the hognose release of the PiTubeDirect software, the answer is yes, because support has been added to use the Raspberry Pi as a second frame buffer. And there's even a VDU driver for it that will emulate all the standard VDU calls that the BBC operating system has to draw graphics and set colours and screen modes and so on. So I can switch over to that by using the command pivdu2. on the ARM native coprocessor. If I'm using the 6502 coprocessor, there's a different command to install a wedge to make that happen, but this is what you use on the ARM. And if I switch over to the Pi's video output, you can see a kind of test card, but if I push return to run that command, I've now got a prompt at the bottom, and I've got a nice display there that's in 640 by 512, which is more resolution than you could have on the BBC. And you can also see it's blisteringly quick compared to the BBC. It also supports all the standard things like the 80 column mode on the BBC. It supports the teletext mode with all the different colours and so on. And I can even run the twin editor because it supports it enough to run things like that. And you can see that it's nice and snappy. So let's exit out to basic, run the program, and execute the code. And there's the 3D10 print running on the ARM in the PiTubeDirect and using the Pi as the video output. And you can see it's a little bit quicker than the BBC. You might not believe me that that's actually running correctly, but if I push break to stop it, you can see it is indeed displaying the effect that the 3D10 print program does. Now when you push break, the BBC reverts to using the internal frame buffer on the hardware itself, the 8-bit hardware, so it will always flip back to that, and if I want to switch back to the Raspberry Pi I need to issue the PiVDU2 command again. So there you go, that's the ARM version of the 3D10 print program. It assembles to 179 bytes long, which is 20 more than the 6502 version and 31 more than the Z80 version, which I think is pretty impressive considering all the instructions are 32 bits long. If you didn't like that or have any comments, then drop them below. Just bear in mind that I had to learn ARM assembler to write this program, and it's the first one I've ever written in ARM. If you did like it, thanks for watching. Sorry about the long video, but I hope you found that interesting and maybe even useful. See you next time.